The first section is all about the population proportion. So we're going to be focusing on the random variable population proportion. Remember, we talked about that last time in chapter 8. And the key ideas that are going to come to play in this section are confidence. This has a specific meaning, so keep that in mind. What do we mean by confidence? And then specifically confidence interval for population proportion. And we want to figure out how to interpret it, and we also want to figure out how to compute it. And the homework is listed here. You can get started after we go through this. I do want to give you a heads up. Starting with this chapter, things start getting a little heady, but they also start getting a lot more interesting. So things are going to get pretty cool pretty fast. Okay, so the main idea in this section is suppose we have a parameter that I'm going to call beta. So this is just the Greek letter beta. It looks like a B, except you take the side and you make it longer. And B is a statistic that's estimating our parameter. Okay, how do we judge how good of an estimate B is? So this is kind of the main question for this section. So this is what you want to kind of have in your mind. Okay, so for starters, what we're going to do is our example here. It's not uncommon when you're hearing things, you're hearing about studies done, you're hearing about statistics floating around, to hear a line like this. We have 95% confidence the proportion of houses in the US with at least one pet is between 0.651 and 0.709. So there's a couple things that I want you to pull from this example. One is this word confidence. So that's the idea there. The other one is that we're not actually using a specific statistic, a single statistic to make this estimate. Instead, we're using a range of values. So the idea is here we have an interval of values from 0.651 all the way up to 0.709. And what we're saying is that we have this certain amount of confidence that our actual proportion, now keep in mind the proportion of houses in the US with at least one pet, this is your beta. This is your parameter. This is some number. And you could figure it out if you asked everyone in the United States, or at least you interviewed one person from each house, is there a pet there? So this exists. It's out there, but it's unknown. And what we're saying is we have this certain level of confidence, whatever that means, that it lives in between this, in between these numbers. So somewhere in this interval. So what you want to keep in mind is what do we mean by confidence? That's the first thing we're going to talk about. Why is the estimate given as a range of numbers instead of just a single number? And how do we determine all of this? So those are the things we're going to answer in a second. So we'll start with this idea of confidence. And I'm going to start with a little bit of an analogy. Suppose you have a target in front of you and you're trying to hit it, and you are given a baseball, and you're asked to throw the baseball, and you're asked to hit it. Well, how much confidence do you have that you'll actually hit it? So you kind of have to think about that. Maybe you would put it in terms of a percentage. Well, let's think about it in another way. So think about it in terms of this question. How many times out of 100 throws do you think you could hit it? So, if you want to imagine it's 10 feet away, you're given a baseball, you have to hit it. How many times do you think you could hit it out of 100 times? And it's going to vary from person to person. You might have baseball players who are good at throwing baseballs and things like that. But let's just choose kind of a general idea. So you have a certain level of confidence, that's fine. Now, suppose someone gave you a marble and asked you to hit that same target. Do you think your confidence would raise or lower? It probably would lower because that marble is a lot smaller and it's harder to hit objects with that. Now, suppose you were given a volleyball and asked to hit that same target. Well, all things being equal, maybe you're not good at throwing volleyballs for some reason and you're better at throwing baseballs. But all things being equal, your confidence would actually raise because the volleyball is bigger. So you have a higher chance of hitting that. And again, think about this in terms of, if I threw this or made this throw 100 times, how many times do you think I would hit it? That's the idea of confidence. Okay, so let's kind of speak in math terms, and we'll get back to that example in a second. So what we're using here is we're using just the letter P as our population proportion. We're going to stick with that throughout. That's our parameter. That's what we're trying to guess. It exists, but we don't know what it is. And P hat is going to be the sample proportion. Remember, the sample proportion is two things. It's a random variable, so it's a variable. It changes based on the sample you choose. But if you pick a specific sample, you're going to get a statistic that's going to estimate your parameter. Okay, so if you stick with a specific sample, you're going to get a number that's going to be an estimate for this. Okay, well, remember, P can be any value from 0 to 1. So P hat has to be a continuous random variable. So when we say it's continuous, we're referring to the random variable. All right, so back to our example about cats, or not cats, pets. I just have cats. You might see them later. So we have that houses in the US with pets. There's a parameter that exists that tells us exactly how many, what the proportion of houses in the United States are with pets. It's just the number of houses with pets divided by the number of houses in the United States. Well, maybe we're able to get the number of houses in the United States. We could count that up. Maybe some census data has that. But if we wanted to know this number up top, the number of houses with pets, we would have to go to every house and ask, do you have at least one pet? And that would get tedious and that would get difficult to do. So this is going to be an example of something that exists, because this definitely exists. There is some number out there, but it's unknown because we don't want to spend the time to gather the exact information. So what do we do instead? Well, we're going to take a sample. And what we're going to do is we're going to interview 1,000 households. That seems more reasonable than, millions of households. We're going to interview them. And suppose that once we interview them, maybe it's just a questionnaire, 680 of them say, yeah, we have a pet. Then our sample proportion is just going to be 0.68. So that's going to be our guess. Now, how confident are we that our guess was correct? Should be 0 confidence. Now, why is that? How many numbers are there from 0 to 1? Uncountably infinite. So there are too many numbers from 0 to 1. So what do you think in terms of this number being exactly this parameter? It's probably 0. Potentially, it could, yeah. In fact, you could take samples of 1,000 all day and probably never hit that number. Exactly. So what you want to think about this as is this is your marble. This is this small tiny thing that you are trying to throw at and hit your target. And so what's the solution to that? Well, the solution is going to be, instead of using a specific value, we're going to use a range of values. So this kind of answers that second question, and we're going to center them around p hat. And so what we're going to do is we're going to start at this value, and we're just going to add our guess p hat plus some error term, and then p hat minus some error term. So E is error term. Because maybe this wasn't correct, so we want to wiggle it a little bit with error. So the idea here is now your marble is a little bit bigger. You've added some width to it. And so when I throw this interval and try to hit my target, I have a much, much better chance of capturing it. And this is because I can think, when we're talking about continuous variables, I can think in terms of kind of proportions of intervals with respect to, the whole interval. We talked about that, and this kind of gets to the idea of how intervals carry more weight than specific values. All right, so the confidence we have in our interval, this is where this word confidence comes into play, is let's say we took different samples, we came up with different p's, but we kept this length of interval the same. Well, what that's going to do is it's going to shift it around because this is the center of the interval. And our confidence is going to be how many times this thing is going to actually capture our parameter. That's the confidence. And so what you can think about it as is if I took 100 different samples, how many times out of that 100 different samples is the parameter going to land in this interval? If the interval is the same length the whole time, if we still use the same error term. So pictorially, this is how you want to think about it. What we have is we have this line representing our parameter. It's fixed at some point in the x-axis. And this is our first sample. We create our interval, and we throw it, and we try to capture the parameter. And guess what? The parameter is captured. Works out. And now we do it with the second one, and we, again, capture the parameter. We hit it. Now, what about P3? P3, we don't hit it. It lands outside there. And then P4, we capture it. P5, we capture it. So if we were to compute the confidence of this, again, I don't want to draw 100 lines, but what we would say is we would say, well, 4 times out of 5, we capture this, or this is, 80% confidence. So our methods have an 80% confidence of working if this, picture represents something. Okay, one thing I want to point out is when someone says we have a 95% confidence that the parameter is in this interval, that does not mean that there's a 95% probability or chance of the parameter being in that interval. Because again, remember, the parameter exists. It is a specific number. And once you specify that interval, once you don't keep it changing, once you pick it, then the parameter is either in it or not in it. And so there's either a 1% chance that it's in it, or 100% chance, a 1% or a 1 probability, or a 0% chance, 0 probability. So keep that in mind. That's a very, very important distinction, and sometimes a big thing that people get mixed up when they think in terms of confidence. And I'll point that out again when we do some computations. Okay, so now what we want to do is we want to assume that our random variable, our sample proportion, p hat, is normally distributed. And so one thing we know is that just needs to be a certain assumption satisfied on your sample size, the sample size that you're taking. Now, one thing to keep in mind is we can always, assume that as long as it satisfies certain things, that it's normally distributed, and that follows from the central limit theorem. So again, we're using the central limit theorem as kind of the backbone of our study. Now, recall that for p hat, it actually doesn't matter if it's normally distributed. The expected value of p hat is always p. It's always going to be this parameter that we're searching for. So we can draw the distribution of p hat this way. And the first step we're going to do is we're going to first choose how much confidence we want. And what we're going to do is once we specify that confidence, we're going to look at our distribution and we're going to go out an error term from p, so p plus e, and p minus e, and we're going to go out enough so that this shaded region here, the percentage shaded, is going to be equal to our confidence. So what we want is, remember, we're specifying the amount of confidence we want. So for example, if we want 95% confidence, that's a very common confidence to hear, you want to make sure that you go out enough from your p in both directions, kind of an equal length in both directions, so that the shaded region is 95% of the area under the curve. All right. So what we're going to do is, if C is the confidence proportion, that means that C is just going to be equal to your confidence divided by 100. In other words, C is just going to be the area, shaded area. Or at least the value of the shaded area. So it's going to be the confidence divided by 100. Remember, the confidence we usually put in terms of a percentage. And so if you want the proportion of it, you just divide it by 100. All right? So if that's going to be the case, what we want to do is we want to ask ourselves, what's the probability? So here I'm using capital P for probability, that our random variable is going to be between our parameter minus the error term and our parameter plus the error term. Well, the probability that given a specific sample size, I land there, that's going to be C. Because remember, C is going to be that shaded area. All right, well, let's just take this inequality here and let's subtract p hat and subtract p from all three of these, and what you're going to get is that's going to be negative p hat minus e is less than or equal to negative p less than or equal to negative p hat plus e. So all I've done is I've subtracted p hat from all pieces, and then I've subtracted p, and I'm left with this. So this is actually an equivalent inequality. All right, now if I multiply this all by -1, I'm going to get an equivalent inequality that's going to say p hat plus e is greater than or equal to p is greater than or equal to p hat minus e. So you multiply all of these terms by -1, and then you flip the inequality. But what is this saying? This now says that here you have your random variable, and you're saying that the random variable plus e, random variable minus e, p is going to live between that, is equivalent to this, is equivalent to this. And when you have this, this is going to imply that the probability your choice of sample lands somewhere here is C. So this is where we get the confidence interval. This is how we determine that if we add an error term, if we subtract an error term, we get a specific confidence there from this inequality here. And so what we can do is we can say that the probability P is in the interval P hat minus E, P hat plus E is C. Now, I know this sounds really weird based on what I just said, that, well, given a specific interval and a specific parameter, the probability is either 1 or 0, but here I'm saying it's C. Important thing to keep in mind is we haven't chosen an actual sample yet. We're still thinking of P hat as being anywhere on this curve. And so what's happening here is this interval changes based on the sample. So again, when we say the probability P being in this interval is variable. It changes based on where you're at. All right, so again, warning, P hat is a random variable here. So again, keep that in mind. We're talking about this as a random variable right now. We haven't chosen a specific value. Okay, so we're getting closer to determining what this E is. So what we're going to do is we're going to take our distribution here and we're going to normalize it. And that's going to help us solve for what this E should be. Okay, so if we normalize it, if we send it through this thing that says, well, this is p hat minus the mean over the standard deviation of p hat. So remember, this is the mean of p hat. The mean is p. Well, remember, this z is going to have a mean of 0, always. And what we're going to get here is we still want that kind of same shaded region. And then what we want here is, well, if we plug in the value where p hat is equal to p plus the error term, you're going to get p plus error minus p over the standard deviation of p hat, which is just equal to E over the standard deviation of p hat. So this value here is just our error term over the standard deviation of p hat. And then since this is symmetric, this has to be negative the error term over the standard deviation of p hat. So that's what these are. So again, keep that in mind. And if we look at this area that's non-shaded, kind of the complement, and we call that area alpha, then notice 1 minus our C, our chosen confidence proportion, that's going to be equal to alpha. And so what we can do is we can then say, well, this particular thing has to be alpha divided by 2 because of symmetry. And so what we're going to get is E over standard deviation of p hat has to be equal to Z at alpha over 2. Okay, so remember when we write Z sub something there, that means that's the Z value where the area to the right is equal to this sub value. So we're saying this is the Z value where the area to the right is equal to alpha over 2. All right, so what do we get? We get that the error term, E, has to be equal to standard deviation, p hat, times Z, alpha over 2. And this now gives you the error term. And recall that the standard deviation of p hat, this is going to be the square root of p times 1 minus p over n, where this is the sample size, now there's a problem here in that we don't know what p is. So again, p is unknown. So what we have to do is we have to replace p with the best estimate. And since the sample standard deviation is going to be, or since the sample proportion is going to be very close to p, just because we're assuming it's normal, this isn't going to vary too much from that. So it's a good estimate. So we're going to use that. So what I want to do is I want to give you the punchline to all this. So if we have a sample size of n, confidence C times 100%. So remember, you choose your confidence, you choose your sample size, and sample proportion p hat, the confidence interval for our population parameter is going to look like this. It's just going to be the interval from p hat in the center, and then you're going to get p hat minus the error term, p hat plus the error term, and this interval is just p hat minus e to p hat plus e, where e, so this is kind of part of the punchline, e is going to be equal to z alpha over 2 times the square root of p hat, 1 minus p hat, over n, and alpha is equal to 1 minus c. Okay, so what I want you to take away from this is the punchline. This is how we're going to be computing these things. E is equal to this, alpha is equal to this. So again, we're going to be given a sample size, we're going to be given a certain confidence, and we're going to be given a sample proportion because we're going to choose a sample. And so how you compute the confidence interval is going to be, well, it's just going to be p hat minus e, p hat plus e, where e is going to be computed this way. We can find these different values because we know what that is, and we can find alpha because we're given the confidence. And once we find alpha, we can figure out what that z value is using tables or technology. So we're going to come back and see that in a second. So we return back to our running example of the number of households in the US with pets. Okay, suppose we want a 95% confidence interval for the number of households in the US with pets. We randomly sample 1,000 households and 680 have pets. Okay, so this is going to give us, remember, this will give us our p hat, our specific p hat, which is 680 over 1,000, or 0.68. Perfectly fine, 680. Let's write it like that. Now, one thing you want to do is a very, very important first step is you want to make sure your normality assumption is satisfied. So we want our random variable p hat to be normally distributed. So in order to do that, we have to make sure that the sample size, so remember n is the sample size, n is going to be 1,000 in this case. This is the sample size. We want to make sure that n times probability minus, or times the proportion minus 1 minus the proportion is greater than 10. And remember, we don't know the actual proportion, so we have to use p hat. But again, p hat is going to be very close to p, so this is the best thing we can do. So you use p hat, and you find that this number is greater than 10. So let's just check that this number is greater than 10. Well, if you have, I didn't write this down, but let me grab my calculator. It's over here. If I throw 1,000 and I multiply it by 0.68 and multiply it by 1 minus 0.68, which is going to give me 0.32. So 0.32 times 0.68 times 1,000. And you get 217. So this is definitely greater than 10. So that's perfectly fine. We don't have to worry about that. So this works out. You also have to check that n is less than or equal to 5% of the entire population. Now, you don't need to check that because we don't know the exact population of households in the United States, but we know that it's probably in the millions, and 1,000 is definitely less than 5% of that. So you just have to have a good reason for that. You have to reason it. All right, so the reason for this assumption is you want to make sure that your samples are going to be independent. And so you have to satisfy that independence criteria. Okay, so once we've done that, we can get on to solving for things. So this is going to give us our p hat. So again, p hat is going to be 0.68. We want 95% confidence, so that tells us that c has to be equal to 0.95. And so 1 minus c is going to be 0.05, and this is equal to your alpha. And then alpha divided by 2 has to be 0.025. So you can work that out. And so what it means is when we're looking at our normal distribution, you want C to be this region here, and you want alpha to be the shaded region. So remember, the shaded region here is alpha. Those are kind of the bad regions that you don't want. You want your parameter to kind of be around here. And so if we're in a standardized normal distribution, then this part here is just going to be z sub alpha over 2, and this part here is going to be negative z sub alpha over 2. And so if I look at table 5, which tells me a correspondence between z values and so this is from table 5. Table 5 is going to tell me a correspondence between z values and area to the left of that z value. Well, if I look up and I say, well, I want this area to be 0.025 because there's symmetry there, then it's going to tell me that this is going to be about negative 1.96. And so if I want this value here, that's going to be the negative of negative 1.96. So this z value is going to be 1.96. And so if I want the error term is going to be z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. So this is a multiplication. So when you plug in the numbers, you're going to get 1.96 times, this will be 0.68 times 0.32 all over 1,000. And then you take the square root of that. And what you should get is approximately 0.0289. That's what I got. And so my error term is going to be 0.0289. And so if I'm looking at my interval and I want the confidence interval, this is going to be my p hat. This is going to be my guess, 0.68. And then I'm going to go out p hat minus e and p hat plus e. And it turns out that this value is going to be about 0.651, and this value is going to be about 0.709. So my confidence interval is going to be from 0.651 to 0.709. And that's going to be the solution. And so when we say we're 95% confident that our parameter lands between there, this is what we mean, and this is how you compute it. And I know it's a little complicated, but if you just take it one step at a time and you look through that punchline, that's going to be what is going to work out for you. Okay, the last thing for this section is suppose we want to make the error smaller. So in this sense, what we're doing is we're thinking of a problem like this in terms of suppose we're given a specific error, and maybe we don't like the error that we're given when we compute a certain confidence and stuff like that. And we'd like to make it smaller, so we'd like to affect it and change it in some way. Well, one way to do this is to lower your expectation of confidence. Because this is a lot like saying, like, well, if you just don't want as much confidence, you can use a smaller ball to try to hit your target. Maybe that's not ideal. Maybe you want to keep your confidence high and you want to keep your error small. So how do you do that? Well, one way you can do that is you can change your sample size, and you can make your sample size larger. So in doing this, one thing you want to remember is you want to keep that sample size less than 5% of your population. But the idea is, suppose we want a specific error outcome, and we want to figure out how big our sample size should be in order to change that. Well, all we have to do is we have to solve for the n and assume we have e here. So if we solve for the n, what we're going to do is you can divide by the z. So you have your error divided by z alpha over 2 is equal to the square root p hat 1 minus p hat over n. And then we square both sides, and we're going to get p hat times 1 minus p hat over n is going to be equal to, well, it's going to be equal to e over z alpha over 2 squared. And then I'm going to flip that, n over p hat 1 minus p hat is going to equal z alpha over 2 over e, all of that squared. And then you're going to get n is equal to p hat times 1 minus p hat z alpha 2 over e squared. All right, so this is what your sample size should be. And then what you want to do is you're not always going to get an integer. So you want your sample size to be the next highest integer. So always kind of raise it to the next level. Because, again, if you choose a larger sample size, that's just going to decrease your error a little bit more. So maybe your error won't be specifically that value that you were aiming for, but it'll be smaller, which is okay. Now, one thing you might notice is we have this p hat here. What if you want to change your error or aim for a small error, but you haven't done any sampling yet? You haven't done anything to guess what your proportion should be. You want to pick that. Well, the way you do that is you just figure out what is the largest this value can be. And you have to use some calculus to figure that out, but I'm going to tell you that the largest this value can be is when p hat is equal to 1/2. And so if p hat is equal to 1/2, then 1 minus p hat is equal to 1/2, and when you multiply them together, you get 1/4. So if p hat is unknown, because you haven't done any sampling yet, no sampling yet, then use n equal to 0.25 times this term here. And so remember, this is again when you want a specific error, when you have a specific error in mind and you want to keep within that.
All right, I'm having a little bit of a tough time teaching right now. As you can see, she won't get off.